So I'm going to talk about things, some of which people have already talked about. So I think we're familiar with some of the basic ideas. But I'll start at the beginning. So I'm going to talk about prethermalization in aperiodically driven systems. But as is customary, I guess, before talking about aperiodically driven systems, let me just give a very brief overview of periodically driven systems. This has been already talked about. So periodic driving provides us with a very powerful way, a powerful tool to control the dynamics of quantum systems, quantum antibody systems, and in the last 10-15 years it has emerged as a method to really realize various novel non-equilibrium phases of matter like Floquet anomalous topological insulators or discrete time crystals and so on. But Floquet systems suffer from one major drawback, and that is that interacting periodically driven systems absorb energy from a drive and it heats up. And the reason for this is that there is no energy conservation in periodically driven systems. So this is something Chowdhury talked about. So, and because of this absence of energy conservation, what happens is that your system will almost always heat up to a featureless infinite temperature state with zero entropy, with a featureless infinite temperature state with maximum entropy. So there are some remarkable exceptions to this, like many body localized systems or systems which remain integrable even under driving. But generically, many body systems under periodic driving is going to heat up. So, but while this looks pretty drastic, we all know that this is not the end of the story. And what you can do is there are other possibilities. And in particular, if you have high frequency driving, then high frequency driving can lead to prethermalization. So what is this prethermalization and why does high frequency driving lead to this? So let me talk about it a little bit. So the idea is that if you are driving a system with a frequency omega, which is much larger than the local frequency scale in the system, then what happens is that in order for the system to absorb energy from the drive, in order for the system to absorb energy from the drive, it involves several local rearrangements that need to happen in order for this energy to be absorbed. So for instance, let's say that you're driving with a frequency omega and lambda is the local energy scale, then you have around n local rearrangements, which is n is proportional to omega by lambda, and this is a process which is whose amplitude is exponentially suppressed with omega by lambda, and this leads to an exponential suppression of the heating rate. This of course is a schematic of how this works. We can put this on very rigorous footing, but this is sort of the idea of why Floquet prethermalization happens, and Wenwei has this extremely nice review on this, which if you want to look it up. So apart from, so how do we characterize prethermalization? So of course one thing that we're saying is that we do not want the system to absorb energy, but really the way to characterize it is that if a system undergoes prethermalization, then it goes through there's a long period of time during which the system's entanglement entropy does not grow. Right? So there is effectively static thermal behavior, and you can describe the dynamics of this system by one effective Hamiltonian within this region. So this is a characteristic of Floquet prethermalization, and this is what we would require of prethermalization, that even if the entanglement entropy grows initially, there is a long period of time for which it does not grow, which scales with exponential omega by lambda, and after which it grows. Okay, so this is the story of Floquet prethermalization in quantum systems. You can ask this question of what happens to this for classical systems. I'm going to talk about spin systems. So here when I say classical systems, what I mean is taking the spin going to infinity, the s going to infinity limit. And if you do that, you can also show that the energy absorption rate still can be exponentially slow for a classical spin system. But there is one caveat, and the caveat is that the dynamics of these classical spin systems are generally chaotic, and the way that you would rigorously establish the existence of a prethermal phase in quantum systems sort of relies on Lieb-Robinson bounds, which do not operate here. And because of this, it is difficult to say rigorously that you will indeed get prethermalization in the sense of having a region where your entanglement wouldn't grow, the equivalent of an entanglement wouldn't grow, and you could describe the dynamics by some effective Hamiltonian. So one way to characterize, since we of course cannot have an entanglement entropy for a classical system, one way to characterize what's happening in a classical system is to look at what is called a decorrelator. So a decorrelator is sort of the classical equivalent of an out of time ordered correlator. The idea is that you start off with two systems which are two copies of the system which are very, very close, and you let it evolve and you want to see what's happening. Okay, so if the decorrelator grows very fast, it would mean that the equivalent thing would be that in the quantum system would be the out of time ordered correlator growing very fast, and consequently the entropy or entanglement also growing very fast. So, So here what is found interestingly is that in many cases what happens is that the decorrelator, even though it initially grows fast because of the chaotic nature of the system, it can grow through a region where it essentially plateaus before it heats up again, and this thermalization time here also scales with e to the power c omega. Okay, so this between this energy absorption being slow and this plateauing of the decorrelator, you can establish prethermalization in classical Floquet systems. Okay. So my talk, of course, is not about Floquet. My talk is about aperiodically driven systems, and so the next step that we want to take is we want to go beyond the notion of perfectly periodic driving, and we want to ask this question that are there other forms of driving where you can still get prethermalization? And there are two such forms which are now well known, which was mentioned by Marine yesterday. So one is quasi-periodic driving, and the second is what's called random multipolar driving, and I'm going to talk actually a little bit about both today. So the idea is that if you drive a system completely noisily, then it just generally heats up, and there is no reason for it to go through a prethermal plateau. However, if your noise has some kind of structure, if your aperiodic drive has some sort of a structure, then the system can go through a prethermal phase. And what's been recently shown by a series of works from Roderich group at PKS is that indeed if you have a drive which has a particular form which is called multipolar, then you can go through prethermalization. So what is a multipolar drive? Let me take some time to tell you about it, because a large part of my talk will focus on multipolar drives. So the idea is the following. Let's say that you have a Floquet system which is composed of, where the Floquet unitary is composed of two parts. So you write the Floquet unitary as u minus times u plus, like this. Okay. So a Floquet unitary would be u minus, u plus, u minus, u plus, u minus, u plus, and so on. A random drive here would be some random combination of u minus or u plus. Okay, so these minuses and pluses occur in some random sequence. One way to build a structure here is that you say that I'm going to have randomness, but the randomness will be in terms of dipoles. So what I mean by this is that if you have a plus, you can have two units which are randomly which are placed randomly, but these units are, instead of being minus and plus, these are plus minus and minus plus. So these look like dipoles. So plus minus looks like this, minus plus looks like this, right? So this is an example of what is called a dipolar drive, and you can now sort of generalize this idea to get to what is called a multipolar drive. So this is the mathematical construction of this. So the mathematical construction is that you have for any multipolar drive, for any order n multipolar drive, you have two unitaries which are randomly distributed. But the way that these unitaries are constructed is that you take, let's say that I want to construct the dipolar drive. So what you do is you take the n equals, which is n equals 1. So you take the n equals 0 unitary of plus and minus, and you combine them to create the new un plus. And similarly for un minus, you do the same thing. So for dipolar drive, then u1 plus becomes plus minus, and u1 minus becomes minus plus. You can repeat this exercise. So this is a quadrupolar drive. It becomes plus minus minus plus and minus plus plus minus and so on. Okay? And if you do this, you will find that this procedure gives you prethermalization. It gives you a prethermal plateau and if you have a drive with n random multipolar correlations, this sort of scales as omega to the power 2n plus 1. And if you continue doing this process all the way up to n equals infinity, you get a totally deterministic drive. This is a very structured drive. It's a quasi-periodic drive which is known as a Tomaz drive. And for Tomaz, you can argue that the scaling goes as this form of exponential c log omega square, which is faster than any power law. So this, so this is up to now. I've talked to you about the phenomenology. Let me tell you why this kind of multipolarity works. The reason why the multipolarity works is the following. If you took a totally random drive and you took its Fourier transform, then you would have Fourier weights uniformly across the spectrum. And because of this, what would happen is that the system could absorb frequencies of all possible frequencies, and that it would heat up. What happens is when you have multipolar drives, then you have a suppression of frequency of the Fourier spectrum at low frequency, suppression of the Fourier weights. And because these are algebraically suppressed, and because of this, you can, at least for small n, you can argue that using Fermi's golden rule, that if the system absorbs energy from each mode independently, then there is a scaling of omega to the power 2n plus 1 that arises out of this. Right. So this is all. So this is what's been shown for these kind of multipolar systems, and there's sufficient numerical evidence to support a lot of this. And at least for short-range interacting quantum systems, this has been fairly well established. Okay. So we want to ask two questions on top of this. So the first question that we want to ask is, what happens to this prethermalization in the classical limit? Because we already know what happens for Floquet in the classical limit. So this is a natural question to ask here. The second question that we want to ask is, can we employ these kind of random multipolar drives to realize some sort of non-equilibrium phases? Right? So can this prethermalization be utilized for something? So these are the two questions that I will attempt to address in my talk. Okay? So with this, let's run to the first question. So we're going to do multipolar driving on a classical spin system. So here is our model. So we take classical spins on a square lattice, and this is subjected to multipolar driving. So here, of course, there is no Floquet unitaries, but you have two Hamiltonians which dictate how the system will evolve. So the two Hamiltonians are these Hz and Hx. So Hz is a standard Ising model Hamiltonian where you have Ising interactions and a longitudinal field. Hx is the transverse field. Okay. So a random drive would be one where this Hz and Hx are independently distributed. Then dipolar one would be Hz Hx or Hx Hz, and you can do quadrupolar all the way up to n equals infinity. And so what we want to do is we want to examine the heating rate and also the growth of the decorrelator to find whether the system can have prethermalization and what is the nature of this prethermalization. So how do we do any of these calculations? So because of this discrete nature of the drive, what you can do is for each part of the drive, whether you're evolving by Hz or Hx, you can analytically actually integrate the Hamiltonian. You can integrate the equations of motion to obtain a map that takes one spin configuration to another, depending on whether it's Hz or Hx. So Hz corresponds to having Hx corresponds to having, of course, an magnetic field along the x direction, and if you have Hz, then you have an effective magnetic field along the z direction, which has both the longitudinal field as well as this term which arises due to the interaction. So basically every spin sees its neighboring spins, and that gives rise to an effective field. This part, of course, makes this evolution nonlinear. So with this, we set forward and actually run the computations for finding whether the system can show some kind of prethermal phase or not. So how do we do the calculation? So what we do is the following. We start off by initializing the system in some initial state, and so in principle, what we want to do is we want to start off this thing with some kind of initial energy density. So what we do is any spin is given some angle theta from the z direction and some uniform and some angle phi in the xy plane, and we take an ensemble of initial conditions where this theta is chosen from a Gaussian given between 0 to 2 pi w. This w is something we can change, and this phi is uniformly given from 0 to 2 pi. And the other thing that we can do is we can make these sort of nail ordered or antiferromagnetically ordered, or we can make these ferromagnetically ordered. So this is sort of the first initial state that we would start off with. And we find that indeed this spin chain exhibits prethermalization, and as we go from n equals 0, 1, 2 all the way up to infinity, you do see that the prethermal plateau lasts longer and longer. This is true both in terms of the energy as well as in terms of the decorrelator. So okay, so this shows prethermalization, but we have to also look at what is the time scale over which this prethermal plateau remains and what is the time scale for this thermalization. So to do this, so we look at how long does this decorrelator take to reach a value of a very high value, its saturation value for different frequencies, and then we fit that thermalization time to some sort of power law, and we find that at least for small n, this power law is actually 2n plus 2. So a prethermal plateau appears with this kind of power law. So this power law is different from the quantum power law. So for the quantum system, this power law was 2n plus 1. Here we found it for 2n plus 2. And we did it for initial states which were similar to the ones that were considered for the quantum system. An immediate question arises that is this true for all initial states? Or how does this change if we change the energy density? So this, I don't know what happens for the quantum system actually, because it's not been done, but we did this and we found that there is a transition at some critical energy where the power law goes from being 2n plus 2 to 1. So this exponent shows a transition, and this is very typical of prethermal systems. And so, if you are below this critical energy or energy density or above this critical energy density, you do not, you see a good prethermal phase, and then here, everything just falls down to this value. And we can see this even if you look at what happens for the decorrelators. If you are here, for instance, at this A or D where you have good prethermalization, then you see that as a function of n, you get better and better prethermal plateaus. However, if you are right in the middle here, then there is no good scaling with n for all, at least for small n's, even the multipolar drives behave the same as a random drive. Okay. Now, so this is the case for these multipolar drives. So the next question, of course, is what happens when you go to the Thue-Morse limit? And we found that when we go to the Thue-Morse limit, again, there is a prethermal plateau. Here, however, again, the scaling of the thermalization time is different, and notably the scaling of the thermalization time in the Tomaz case is actually exponential, much like the Floquet case. So even though this is a quasi-periodic drive, so it is actually more noisy in a sense than a periodic drive, the thermalization time still scales exponentially. These are of course for special initial states, so we looked at it as a function of initial states. And what we found was that while as you increase the energy density, the thermalization time seems to sharply drop around a certain energy density. If we look closely, the time that it takes to thermalize, that still seems to scale exponentially. So this exponential scaling of the thermalization time seems to occur for all energy densities, even though of course there are some critical energy density below which this falls completely, this thermalization time itself falls completely. So this brings me to an end to this part where we examined multipolar driving for classical spin systems, and we found that just like the quantum spin systems, the classical spin systems do exhibit prethermalization, albeit with different behaviors. In particular, we found that for ferromagnetically or antiferromagnetically ordered states, this scales as t to the power 2n plus 2. We know for quantum this scales as 2n plus 1. And we find that this exponent alpha undergoes a transition from 2n plus 2 to 1 as a function of the energy density. For the Tomaz driving, the lifetime of this prethermal plateau scales exponentially. And this shows that while for Floquet, the behavior, the thermalization time, that behavior was very similar for the quantum and the classical cases. If we go beyond periodic driving, quantum and classical regimes may be quite different. Yes.
I was basically just going to ask if you have any understanding of why that is, why at these very long times and infinite temperature should there be any difference between quantum and classical in this way?
Oh, okay. So I want to say the following, that if you take the quantum model, if you take the classical model, you can map this to a very weird long-range quantum model. And so what we're doing is, if we take the short-range classical model and if it can, it maps to a long-range quantum model, then maybe the long-range nature of that quantum model is essentially that changes the nature of things. So what we have to do if we really want to understand this is we would want to actually study properly the long-range quantum model to see what's going on. The better way to say this is the following, that for at least for certain initial states where things don't match at all, this is true. For the middle of the spectrum, I'm not sure how to understand this, but at least for, let's say, if you have a ferromagnetically or antiferromagnetically aligned state, there you can do this exact mapping to basically your S itself starts acting like another dimension and gives you so you have a classical model, but then you have the S acting as another dimension, and there is some long range interaction along that dimension. So it's a very peculiar quantum model that you can map the classical model to. So in some sense, these models can be quite different, while the nature of the prethermalization would remain the same, and you can set some rigorous bounds on, some rigorous sort of lower bounds that, okay, prethermalization time has to be, greater than this and so on. But beyond that, we can't say much. So that's all that I can say about this. Okay. So good. So with this, we move to the next part, which is I'm going to talk about something called random multipolar time crystals, and this is a slight issue with the terminology. So we'll come to it when I discuss this. Okay. So so the next thing that I'm going to talk about again starts off with the Floquet part, and then we will move to the aperiodic part. So in the recent past, one of the big sort of advances where periodic driving has been very useful is in the realization of a discrete time crystal. So a discrete time crystal is basically a periodically driven system where physical observables oscillate with a subharmonic frequency. So the easiest example is something where you drive a system with a period t, and the system responds with a period n times t, where n is greater than 1. Okay. So if you have period doubling, for instance. And so this is, in principle, if you just ask this, that I want period doubling oscillations, this is not very hard to generate. This is something you can easily do. The main thing which makes realizing time crystals sort of non-trivial is that we want to demand some sort of robustness from these time crystals, which means that this kind of period doubling or period quadrupling, this should occur for a sufficiently large class of initial conditions, and this should also happen, this kind of period doubling should continue to happen even if you make small changes to your Hamiltonian. So it should be robust to changes in initial state and the Hamiltonian. It turns out that that is very difficult to do, and that crucially requires interactions. And the first models for time crystals essentially then relied on many-body localization, because many-body localization enables systems to not heat up. So the idea was that, let's say you have a many-body localized Hamiltonian and you give this a kick at times t, 2t, 3t, etc. Now, if this kick is an exact pi pulse, then you can very easily get a time crystal, because what happens is, let's say you have all spins pointing up, you give it a pi pulse, all spins will point down, you give it a pi pulse, all spins will point up again. But if you move even slightly away from the pi pulse, then instead of period doubling oscillations, you will end up getting beats. So this interaction then plays a very crucial role in synchronizing the system so that you get period doubling oscillations, and you of course then need disordered interactions as well as on-site disorder to sort of evade heating in these systems. Now, after this came about, there have been now many more proposals to realize time crystals in a variety of platforms. I'm not going to talk about many-body localized systems today. Instead, I'm going to talk about a much simpler, albeit slightly fine-tuned place where time crystals arise, and this is a mean field. This is a mean field setup where you have all-to-all interactions between spins. Okay, so uniform all-to-all interactions. So this is subjected to a periodic kick. Okay. And this system can also show time crystalline behavior. Unfortunately, won't have the time to tell you why, but this all-to-all interactions gives this a mean field nature, which prevents the system from heating up. And if you don't make this uniform all-to-all, and if you add a 1 over r to the power alpha kind of thing here, you can still get a pre-thermal time crystal. Okay. So we wanted to take this form and ask this question of, if instead of giving this kick periodically, if I make this kick amplitude aperiodic, what happens to this time crystalline behavior? Do you still get period doubling oscillations, or what, does this just heat up? So this is what we studied. So we make this kick aperiodic, and we took this to come out of some sort of random sequence which would have some multipolarity. And what you find is that if you have a totally random kick, yes, that's a pi pulse. It's just a pi pulse. That's the rule. Yes. So if you have just a random kick, then the system just heats up very fast. But in fact, even a dipolar kick doesn't help too much. But once you have a quadrupolar kick or something higher, then you see that this kind of period doubling oscillations last for much longer. And this is, so this is n equals 2, 3, this is the 2 Morse n equals infinity, and then up here is the Floquet. So why does this happen for at least starting from quadrupolar? So the way to see this is that if you take the kick operator in the model, where we take this as some epsilon tau n, where tau n can, so we take pi, I've taken pi by 2 because this is a SIX or a sigma x, whatever you want to use. So anyway, so if you take tau n to belong to be either 0 or 1, and you choose this from a random quadrupolar sequence, then what happens is that your time evolution is composed of 2 kinds of effective quadrupoles, U1, U0, U0, U1, and U0, U1, U1, U0. And what you can show, and I'm not getting into this too much right now, but what you can show is that in the high frequency limit, these, to a very good approximation, can be approximated to be some u bar to the power fourth, where u bar is an effective Floquet propagator. So you get this using the BCH formula. And when you do this, there are additional error terms that we are throwing away, that we are not considering. So once those error terms start contributing, the system starts heating up. Now what happens is, when you go to any higher order, like octopolar and so on, what happens is some of those error terms get removed, and because of that, the heating for higher order multipolar drives takes longer. And so in a sense, the system can exhibit some sort of pre-thermal time crystal order, but I want to say that I've put this time crystal order in quotes because there is no real time translation symmetry here, because this kick is aperiodic. So there is some sort of an average time translation symmetry that's being broken. So even though I'm using this term, this is, the terminology might be slightly shaky. And if we go to the Tomaz limit, these time crystals are pretty stable. These are pre-thermal, so I checked it for different system sizes. And if you look at, you can also, for this kind of mean field model, you can look at what happens semi-classically in the infinite size limit. And for various perturbations, this kind of time crystalline order stays. What I didn't mention in this talk is that these were, of course, for period 2 time crystals, but in this model you can get various other higher period time crystals, and even those are pretty robust, and then those also come about if you use this kind of multipolar driving. So with this, I want to conclude this part as well, that so these kind of random multipolar drives, it gives us a way to realize various kinds of pre-thermal phases of matter. And in this particular case, we took the example of a time crystal-like phase where the average time translation symmetry is broken. And maybe I just want to mention that while I've used the term time crystal, maybe I'm also looking for a better term to give to this, because usually in a time crystal, you either have a continuous time translation symmetry being broken or a discrete time translation symmetry being broken. But here, what happens is your system response, in a sense, has more symmetry than that of the drive, because the drive is totally aperiodic. So it has neither continuous nor a discrete time translation symmetry. The response has a time translation symmetry. So so to that extent, maybe one needs to think about how to characterize such systems where you get periodic response in the presence of an aperiodic drive. And yeah, so with this, that's all. Thank you for listening. We're open for questions.
So again, like on the first part with the
Yes.
classical model, surely it would be more natural to have a classical model which like is the classical limit of a like nearest neighbor, say, quantum model, which like I thought that the model that you wrote down was, right?
Yeah, so that's what I did. So what I did was I took so basically, okay, so the really good, okay. So I took a nearest neighbor model on a square lattice, right? So this is exactly, and this is of course done because we want to compare to the quantum model, right? So this, where did it go? Somewhere here. Yeah, so this is it. It's a nearest neighbor model. So that thing that I was saying about mapping it to the long range model. So so there's a 2018 paper by Takashi Mori where this is actually explicitly done.
Is it long range in what dimension or in
No, it's
quantum model which you have?
Oh, no. The quantum model that I have is actually long range in 2D only. What happens is, because if you start off with, so you're going to the S equals infinity. So what you can do is you can split the S equals infinity to be several S equals halves, and that forms an additional dimension, sort of. But these are all interacting. So what happens is that you end up getting a 2D long range model, but this is not just the regular 1 over r to the power alpha long range model. This is some very peculiar model. But nonetheless, once you've mapped it to that, you can say some rigorous statements. So you can, for instance, here one of the good points was we could have always said that we would expect prethermalization, but we could not set what is the time that it would take. Okay, so that is a very peculiar long range model. But in general, I mean, but this is a short range model, and we are comparing to a quantum short range model as well. That is the only fair comparison to have, I guess. Right? Yeah.
I guess like putting the long range mapping aside, like I would have just said that if you at infinite temperature and very long times, and like you're approaching something which is thermal, then it would seem like unusual that there would be like a big difference between.
So the infinite temperature exactly matches for the for the random multipolar drive. Actually, the infinite temperature results match. It's only the sort of low temperature results that do not match.
So it's something to do with like some like special ground state properties in the quantum model or something?
If it was just, yeah, so
like,
well, it's not just ground state, I would say, because it happens over a certain energy density, but definitely near the middle of the spectrum, there's no change.
Okay.
It's the same. Yeah.
Great.
Yeah.
Thank you.
Okay, the next one.
Yeah, I have two questions from the first part.
Yes.
One is you showed the Tomaz was the limit of the multipolar drive, right?
That's right.
But I might have missed something but there are two completely different scaling laws of T-thermal in your first part of the talk, right? One
That's
was,
right. That's right. That's
so
right.
do you have an understanding how one goes to the other if one is the limit of another?
This is unfortunately, this is very difficult because what happens is that the way that this is set up, all these are done via some sort of Magnus expansion. And what is done is that for the Tomaz, there is the way that this limit is obtained is by finding the optimal order at which you want to cut off the Magnus expansion. And the others are obtained using Fermi's golden rule. So in a way, those derivations are different, and I don't have an idea, but somehow the authors also never comment on this. So it's something I'm puzzled over. It's a very good question. I unfortunately don't have the answer.
The other question is, can we engineer Fourier spectrum to our liking to create some sort of periodic?
Yes, exactly. So you don't actually need to do this. What you can do very easily is you take a Fourier spectrum, pass it through a Fourier filter. We did it actually. You pass it through a Fourier spectrum, pass it through a low pass filter, whatever you wish, and you can actually sort of make this very general. You can sort of create some sort of profile and change the width of that profile, and through that control the time of prethermalization. Absolutely. Yes.
Thank you.
Okay, one more question back there.
Yeah, so I imagine that when this survival time of the crystal is relatively long, what you see is a time crystal, then a defect, a phase slip,
right,
and then it begins again.
That's right, that's right.
And can you consider them independent in time, like exponentially clock?
So you mean that every time we have a defect, we consider just parts of it, right?
That every time your chances of making a slip are relatively independent and small.
Right. So here, so for this particular model, I have not thought about it, but we've done something similar for a nearest neighbor model, and exactly this is what you do. You want to see that what are the chances that you start having some defects, and those defect regions would grow, and then you want to see some time in which the defect regions essentially take over, and that would be the thermalization time. For this particular model, I haven't done it, but yeah, this is the general way to go. Absolutely.